This is how high voltage looks like.
This happens with the help of a DC to DC boost converter.
This is a very simple diagram where I'm showing you the input voltage, the inductor, the diode, the capacitor, and the load. This is the basic diagram and the most important components that the DC that the boost converter has.
Now, going back to our PCB, let's identify the components that I showed you earlier in the diagram. So, this is the inductor. This is our switch. Theoretically, it's a switch. Practically, it's a MOSFET. It's a transistor that turns on and off very fast. This is the diode, and this is the capacitor. Now, over here, this is the output of the circuit through our load. This is the input voltage that comes from the power supply, and this is a control circuitry that is not shown in the diagram. This is responsible for maintaining the output voltage and controlling the transistor.
This is the output voltage using an oscilloscope. We can see the ramp up. Now we are back at our diagram and let's see where this term ramp up comes. So I will draw quickly a voltage over time axis. Now, I've mentioned earlier that the boost converter in principle boosts up the voltage by collecting the energy released from the inductor during the discharge phase. So here we have a representation of switching cycles on and off. Cycle 1 and cycle 2. Of course, you will have an infinity of cycles. And as time passes, through each cycle, we are adding more and more voltage or energy into our capacitor right here. Of course, at a certain point in time, the voltage will maintain its value. Now we are back to our voltage output waveform, and in this picture taken with an oscilloscope, we can see there is a train of pulses. There we have some, let's call them spikes. These are basically switching cycles where the switch is turned on and off. This is how the voltage on the output is boosted. You can see on the horizontal axis we have the time, and as time goes by the voltage increases more and more. So back to our sketch. Here I have drawn the feedback loop. This is the mechanism which controls the switch in regards with the output voltage. So I've mentioned earlier that the voltage on the capacitor is rising up to a level where it's maintained. Well, this maintenance, let's say, is assured by the feedback loop. Here, the feedback loop uses a signal called PWM. This stands for pulse width modulation. And it does that by controlling the on time for the switch and the off time for the switch. A longer on time means the switch will remain closed for a longer period of time, and this is reflecting as a higher energy stored in the inductor. A smaller time for the switch to be on will result in less energy stored. This is always or how to say, it's dynamically adjusting. So this is all the time there working. If the voltage is too high, it will let the switch open for a longer period of time. If the voltage is smaller, it will maintain the switch closed for a longer period of time. This way, it assures a balance of energy in order to maintain our desired output voltage. Okay, so this is the DC boost converter in action. I have connected to a power supply and to a multimeter to show you guys. So here we can see the power supply is set at 9.7 volts and the multimeter shows 173 volts on the output. So this boost converter is basically boosting up the voltage from roughly 10 volts up to 173 volts. Now, be careful when working with high voltages. Thank you.